picture the graph of a ReLU. If you're picturing what I'm showing on the screen right now, watch this video till the end. I promise you I can change the way you think of activation functions. Before we dive into activation functions, I want to look a little bit into the math behind a forward pass so that we can understand why we need activation functions, but also why I don't think people think of them correctly. The first thing anyone learns about neural networks is the way the forward pass works is you have a series of neurons, each with their own weights, and when you pass in an input vector, the vector gets multiplied by each weight per index. It's a dot product. So what you get is a matrix vector dot product, or something of the format AX. When you do this, you get a linear transformation. If a vector is 1, 1, 1, and then you apply the transformation, it will be exactly double whatever the output would have been if it was 0.5, 0.5, 0.5, or some other linear transformation. You're not going to get some complex, intricate sine wave or something. You can rotate vectors, you can change the angle between vectors, you can map a vector into a higher dimensional space, like you can make a 2D vector into a 3D vector. You can do a lot of different things to vectors. Individual vectors you can do literally anything to. But when you look at the whole set of vectors, you will always be making linear changes to these vectors. It will always be multiplication and addition. So you will never have a nonlinear change. The next thing you'll probably learn about is the bias. Each neuron has its own bias, which when you're taught from a numerical perspective, it's just adding on a number at the end of each dot product between weights. But when you think of it from a whole big picture matrix perspective, you're really offsetting the vector by a certain constant. So if your bias is 1, 1, two output neurons, then you'll move any output up 1 and over 1. And that's the geometry behind the bias. You've probably heard someone say that the reason we need activation functions is without them, neural networks cannot learn nonlinear functions. What that means is that if you have 1 million hidden layers, each with 1 million neurons, and you have a bunch of biases and all that stuff, after all the stuff is done, let's say you have 2 inputs and 1 output, everything will reduce to a 1x2 matrix and a single bias vector that has 1 element. So in other words, 3 numbers are exactly equivalent to probably thousands of gigabytes of data for a massive neural network. What this means in practice is if you are making a loan model and people who are 20 in your data set don't pay back their debt, people who are 60 in your data set don't pay back their debt, but people in their 40s are pretty good about paying back their debt, the network won't be able to parse this because there is no line you can draw through the axis of ages that will cut out 60, cut out 20, and keep 40 while still being a line. So that's why we need activation functions. Chances are, if you're still watching, you've understood most of the things I've said. And even if you don't, you still understand the intuition of, oh, points, coordinate planes, all this little math, because you live in a 3D world. We understand things in terms of geometry. So when you start doing theoretical math concepts and all this like Greek letter notation, it kind of separates things from what they actually mean in geometry, which is where I have a problem with how people learn activation functions. When we look at activation functions, we then switch from this vectorized idea of the inputs of vector, the outputs of vector, and we're applying transformations to the vector to loop through the different elements in an array and apply some complex function with alphas and sigmas to the vector, each component of the vector, and then go back to vector mode. We're flipping and flopping our brains between scalar mode and vector mode, when in reality what we're doing is we're applying a weird transformation, not a linear transformation, not even a transformation, a weird augmentation of a vector onto our output vector before we pass it to the next layer of the neural network. So what I want to do is I want to try and build a vectorized intuition where when you see a ReLU, you think of it as an operation on an entire vector in Rn rather than some loop through the different elements function. What I mean by this is the same way we look at how linear transformations work so that we can understand how a whole layer can affect an input. like we did at the beginning, I want to do the same thing for activation functions. Now, the problem here is two things. When you have an activation function like a ReLU, let's say we look at the vector positive 1, 1. That vector is going to map to itself. So showing the ReLU on just one vector would say, okay, it just maps to itself. That doesn't do anything. If we do -1, -1, then it's going to map to 0, 0. That doesn't really do anything. So we kind of got to show it on a bunch of vectors at once to get a rough idea of what the activation function is doing. But we also run into the issue of something like too many vectors. If we look at all of Rn, or on a leaky ReLU, anything with any negative coordinates gets shrunk, but because we're looking at everything, when you divide by 10, the size of the set is still the same, complex infinity stuff, whatever. We still get the same input as our output. It's just different vectors correspond to different places. So what I decided to do instead was to look at the unit circle, and for most of these, what starts inside the unit circle stays in the unit circle, for pretty much all of them. So it's actually the unit disk, which is all vectors of length 1 or less. So just a circle around the origin. This way we can apply a ReLU to a bunch of different vectors at once. And the way I want you guys to think of this is each point along the circle is a different possible output from a neural network. And obviously everything else in space is also a different possible output from the neural network. We're just looking at a section of outputs to get an idea of how they transform. If you don't quite get what I'm talking about, let's do an example. Let's use ReLU rectified linear unit, or ReLU, which just says greater than 1, it's 1, less than 1, it's 0. And it's that famous graph I showed you at the start of the video. Very simple activation function. When you start with the unit circle and then you apply a ReLU to it, you get this first quadrant unit arc and then a line along the x-axis and a line along the y-axis. And if you think of this as affecting a vector, what we just did was we killed off 3/4 of the information we have in the vector space. Most people intuitively think of ReLU as losing half the information because you can assume half of numbers are going to be over 0 to start, half numbers are going to be less than 0, and then as the neural network trains, it trains around the ReLU. But that's how most people think about ReLU. But when you look at it from this two-dimensional vector approach, you see that we actually lose 3/4 of the possible output vectors. And then if you make it n-dimensional, so you lose 2 to the n minus 1 over 2 to the n possible vectors from your vector space. Now, this isn't me trying to say that this is a flaw with ReLU. However, it's undeniable that you do lose a lot of information, a lot of possible outputs when you apply a ReLU. If you instead say, oh, we're going to use a leaky ReLU, then you get to keep a lot of the possible outputs, or at least the information from them. What a leaky ReLU is for anything greater than 0, you just keep it linear, the same as a ReLU. However, when you go less than 0, you apply a hyperparameter called alpha, which just gives a little bit of a slope. So maybe alpha's usually a small parameter, usually like 0.1, 0.01 or something like that. So let's say it's 0.1. So if it's -1, -1, now it's -0.1, -0.1. You're just dividing everything by 10 when it goes negative. Before I get into softmax, really quickly, every activation function you're seeing on the screen, I hand-coded in C++, then applied to an array, and that's how I graphed these circles, which was really fun to do, but this video was pretty hard to make, and all these videos on my channel take me a lot of time to create, so I would really appreciate it if you could subscribe so that this channel can keep growing, so I can keep being motivated to kind of look deeper into things and make fun videos. Softmax is the function that kind of gave me the inspiration to make this video, because softmax depends on all the values. You can't graph softmax with one input and one output. It doesn't make any sense. With softmax, you have a probability distribution where all the values sum up, and then you get some kind of math, I'll put it on the screen, where that math creates a bunch of decimal numbers between 0 and 1 in your vector, where the larger the number, the higher its probability, and if it's a lot larger than the other numbers, it gets a much greater probability than the other numbers. Now, what softmax does geometrically on our unit circle is it takes all the points and puts them all on the line from 0, 1 to 1, 0. Obviously, with the unit circle, the greatest difference you get is negative 1 to 1, so you don't get that far along that line. But if you have the entire Rn plane of R2, you can get pretty much the whole line. You can get the whole line. If you go to 3 dimensions, you get a triangle that goes from 0, 0, 1 to 0, 1, 0, and 1, 0, 0 as its 3 vertices. And as you go to higher and higher dimensions, you get an n-1 dimensional shape where all the points in that shape sum to 1. Like every point, all of its components sum to 1. One of the most unpopular activation functions is called step. It maps everything less than a threshold to 0, everything more than a threshold to 1, and it's just flat line, straight spike up, flat line. And if you look at it on the one-dimensional like input-output graphs we've been looking at all the other ones on, you get something that looks a lot like a sigmoid, which is a pretty popular activation function. You get a little curve up, and yeah, I mean, it looks like it'd be a fine activation function. So then you have people saying, oh, well, if you actually apply a gradient descent algorithm, because it has this one straight up spike, it can't actually fully operate because this has a undefined derivative, and then the rest has derivative 0, so it's not good for gradient descent machine learning. What does that mean? Like, it's like, it makes sense, but at the same time, it doesn't really intuitively click geometrically. So let's apply it to our unit circle. We get 4 points, 4 distinct points. Everything else, softmax created a line. Everything else created another surface. This is giving us points on the plane as our outputs that are like, that doesn't make any sense. You get 2 to the n possible points. And if you think that's good for a machine to learn from complex data, just reducing it to a certain amount of points, think again. Like that's not a good way to learn. Sigmoid's a lot more popular of an activation function. Its function looks like this. Its input-output graph looks like this. Now, when we apply sigmoid to our unit circle, we get something very different from step. We get this little tiny distorted circle-like shape. And if you do sigmoid to all possible vectors in R2, you end up with a square bounded by the 4 points of the step function. Now, it should be noted that most of the points are going to get pushed towards the 4 step points, the 4 corners of the square. Like, that's why our unit circle maps to something that looks like more of a distorted circle than an actual circle, because things are getting pushed towards the corners of the square. But we still get the square. The neural network can still kind of learn to put most of its data points towards the middle of the square or wherever it wants in the square to kind of optimize figuring out whatever pattern it's trying to figure out. So it does work. It's not linear. It has derivatives. It has all this space, and it makes sense and just works for learning. What I want you guys to really take away from this video is, without an activation function, you're just doing a linear regression problem. You're doing a y equals mx plus b problem. You are not doing an actual neural network. You're not doing deep learning. No matter how much you set up a neural network, it doesn't become deep learning until you actually kind of add in some activation functions and make it so the whole thing doesn't linearly reduce to ax plus b. The other thing I want you to take away is that activation functions are not somehow like these one-dimensional, you go into scalar mode and you loop through a list of numbers and apply an activation function, and then you go back into vector mode, do the dot product, add a bias, go back into scalar mode, loop through a list of numbers, go back into vector mode, dot product, add a bias. Like, with a neural network forward pass, you're just augmenting a vector with linear transformations, with addition from a vector, and then with these non-linear, bizarre functions called activation functions, and then back to a linear transformation, to a bias, and then you do some weird activation function that augments the vector, but you're never working on a list of scalars. You're always changing something in vector space. The other thing is, this isn't a tier list of activation functions. ReLU isn't better than leaky ReLU because it covers less volume, or leaky ReLU is not better than ReLU because it covers more volume. Because at the end of the day, a linear activation function is not good. That's how we get to linear regression, and that covers all the volume. And mapping all your outputs to 0, 0 is not going to get you any information either, and that covers no volume. So clearly the best activation function exists somewhere between getting rid of all the volume and getting rid of none of the volume. So nothing I've said in terms of how much information is preserved and all that really gives a solid ranking of an activation functions. It's just a way to think of them as what they might do on a vector, so that when one works better, you might have some kind of idea why it's working better. If you want to see more videos like this, more videos on machine learning, low-level computing, complex ideas, subscribe and watch my other videos. Thanks for watching.